Welcome to the lecture on refrigeration control, presented by Dr. Sam Tawfiq. Today, we'll explore the fundamental principles and objectives of refrigeration systems. Lecture objectives. In this lecture, we aim to recognize the reasons for using control in refrigeration systems and understand the concepts of subcooling and superheating in vapor compression cycles. Why refrigeration control? Let's begin by discussing the importance of refrigeration control systems. These systems are essential for maintaining efficiency and reliability in refrigeration applications. This slide outlines the different types of control systems used in refrigeration systems. Let's go through them one by one. Safety control. The purpose is to prevent damage to persons and components. This includes motor contactors, electronic switches, and pressure switches. Operation control. The purpose is to ensure trouble-free operation. This includes components like the thermostatic expansion valve, oil separator, thermostat, solenoid valve, pressure regulator, stop valve, sight glass, and filter dryer. Capacity control. The purpose is to ensure the right temperature. This includes components like the solenoid valve and thermostat. These different control systems work together to ensure the safe and reliable operation of the refrigeration system. Each component plays a specific role in maintaining the desired temperature and preventing any issues or damage. This image provides an overview of the key control systems in a refrigeration unit, highlighting the three main categories. Safety control includes components like motor contactors, electronic switches, and pressure switches to prevent damage. Operation control covers devices that ensure reliable operation, such as the expansion valve, separator, thermostat, and valves. Capacity control involves the solenoid valve and thermostat to maintain the desired temperature and system capacity. The integrated components work together to enable the safe, efficient, and effective operation of the refrigeration equipment. Operation and capacity control. Deviations in simple theoretical cycles. The theoretical cycle applications meet many problems, which lead to change the expected or calculated values. The deviations occurs in all cycle components as follows. Deviations in compression system. The compressors never can operate at constant entropy. Mainly the deviation toward the increase in outlet temperature. The index of compression, N, is not equal to constant. Leakage internal and external is expected. The suction and delivery valves results in pressure drops. Friction of moving parts. Mixing between lubricating oil and refrigerant. The suction pressure must be less than the evaporator pressure to overcome the pressure drop in piping, connections and valves. The delivery pressure must be increases than the evaporator pressure to overcome the pressure drop in piping, connections and valves. The suction side must take only saturated or superheated vapor. No liquid hazard except deviations in heat exchangers. The tubes of the heat exchangers causes considerable pressure drops. To reduce the pressure drops, the internal surfaces must have minimum coefficient of friction. Also, it can be designed with multi-passes. Tube material must have high coefficient of heat transfer, with minimum wall thickness. Tube may have internal and external fin. The top image shows the internal structure of a thermostatic expansion valve, key component that regulates the flow of refrigerant into the evaporator coil. The bottom image depicts a bank of these thermostatic expansion valves, likely installed in a larger refrigeration system. These valves work together to precisely control the refrigerant flow based on temperature, ensuring efficient and effective cooling. The images illustrate one of the operation control elements described in the previous slide, highlighting the critical role of the thermostatic expansion valve in the refrigeration cycle. Superheating and subcooling. To ensure that the refrigerant superheating and subcooling, refrigerant entering the compressor is vapor, it is necessary to be at temperature higher than the saturation one. This can be done by superheating with different methods. To improve the expansion process, the entering refrigerant must be absolute liquid. Thus it must be at temperature lower than the saturation. Superheating. It can be carried within the evaporator, allowing refrigerant to continue its heat transfer process after complete evaporation. Outside the evaporator can be done using electric heater, atmospheric air at high temperature, or by heat exchange with the hot liquid refrigerant leaving the condenser. Allow refrigerant to contact with electric motor. The refrigerant will be superheated and motor will be cooled. When refrigerant enters to the compressor crankcase, before entering the compressor it will be superheated and the oil will be cooled. The superheating must be limited as it increases the required compressor power. Subcooling can be done using secondary condenser or additional coil to it, using heat exchange with the cold vapor refrigerant leaving the evaporator, using atmospheric air, if it has lower temperature than the hot liquid refrigerant leaving the condenser. The subcooling can be increased as it increases the required compressor power. Examples of refrigeration control equipment. Superheater subcooler, heat exchanger. This image depicts a cross-section of an superheater subcooler, heat exchanger, coil, a key component in a refrigeration system. The coil is shown with numerous parallel tubes, through which the low-pressure, low-temperature refrigerant circulates. This refrigerant absorbs heat from the surrounding air, facilitating the cooling process. The image provides a detailed technical illustration of the superheater subcooler, heat exchanger, coil's internal structure and operation, showcasing its integral role in the overall refrigeration cycle. Mechanical expansion devices. This image depicts a schematic diagram of an expansion device, specifically a thermostatic expansion valve, which is a critical component in a refrigeration system. The valve is responsible for controlling the flow of refrigerant into the evaporator coil, regulating the pressure and temperature to facilitate the cooling process. The illustration provides a detailed technical representation of the internal mechanisms and different sections of the valve, labeled as P1, P2, P3, and P4, highlighting its complex yet precise operation within the overall refrigeration cycle. Electronic expansion devices. This image depicts an electronic expansion valve, a key component in modern refrigeration systems. The device features a digital display that shows the current operating conditions, such as temperature and pressure. The control buttons and interfaces suggest advanced functionality for precisely regulating the flow of refrigerant into the evaporator coil, optimizing the cooling process. As an electronic expansion valve, this component plays a crucial role in the overall efficiency and performance of the refrigeration system by actively adjusting the refrigerant flow based on real-time monitoring and control. Review of simple refrigeration cycle. This image provides a schematic representation of the basic components in a simple refrigeration cycle. The key elements are clearly labeled: the condenser, evaporator, and the numbered connections indicating the flow of refrigerant through the system. The condenser is shown as a central component, with the high-pressure, high-temperature refrigerant flowing into it from the compressor. Not shown. The evaporator is positioned on the opposite side, representing the low-pressure, low-temperature portion of the cycle where heat is absorbed. This simplified diagram effectively conveys the fundamental structure and operation of a basic refrigeration system, highlighting the essential components in refrigerant flow through the condenser and evaporator stage. A pressure enthalpy (pH) diagram for a simple refrigeration cycle is a graphical representation of the refrigerant's thermodynamic states throughout the cycle. The x-axis represents enthalpy, energy content, and the y-axis represents pressure. The cycle typically consists of four main processes: compression, condensation, expansion, and evaporation. Each process is represented by a line on the diagram, connecting the corresponding states. The compression process increases both pressure and enthalpy, followed by a constant pressure condensation process. Expansion reduces both pressure and enthalpy, while the evaporation process occurs at constant pressure, increasing enthalpy. The diagram is essential for understanding the refrigeration cycle's efficiency and performance. Refrigeration cycle with heat exchanger. The provided image illustrates a basic refrigeration cycle with a heat exchanger. The cycle consists of four main components: a compressor, a condenser, an expansion valve, and an evaporator. Refrigerant circulates through the system, absorbing heat from the evaporator and releasing it to the condenser. The compressor increases the refrigerant's pressure and temperature, while the expansion valve reduces them. The heat exchanger, labeled HE, facilitates the transfer of heat between the refrigerant and the surrounding environment. This cycle is commonly used in air conditioning and refrigeration systems. The provided image is a pressure enthalpy (pH) diagram comparing a refrigeration cycle without and with a heat exchanger. The diagram shows the states of the refrigerant throughout the cycle, including the effects of subcooling and superheating. The equations for calculating the work done by the compressor, the heat absorbed in the evaporator, and the heat rejected in the condenser can be derived from the diagram using the properties of the refrigerant at each state. The addition of a heat exchanger can improve the cycle's efficiency by increasing the amount of heat transferred during the evaporation and condensation processes. With my best regards, Dr. Sama Tawfiq.